In that series of videos, I would like to introduce you to the basics of the university maths. We will take off approximately where the school math has finished. But this will be only an approximate start point. Basics of the university maths. Part 1. We start with an introduction into a mathematical logic. Of course, we will only touch the surface, but we will also negate the surface. And for the introductory courses in mathematics at the mathematical faculty of the university, we'll really need only these basics of the logic that we will touch. Introduction to mathematical logic. Well, first let's talk about what is a mathematical statement. Definition. A mathematical statement also called logical statement, shortcut for statement in logical, in mathematical logic. Logical is here, logical within mathematical logic. Mathematical statement is a statement about mathematical objects that has exact interpretation, and exact includes unambiguous, and about which can be unambiguously decided if it is true or false. A few examples. Examples of mathematical statements. Two divides four without a remainder. For The division is of course considered as division in natural numbers, so division with remainder perhaps. And that is a true statement. Right. Another example, 3 minus 4, of course within the integers, gives number 1. This is a false statement. Pay attention, despite being false, this is a mathematical statement. It's just put us parentheses here. Right. It is a mathematical statement, but its truth value that could be another definition. Being true or false is called being assigned a true value by mathematical statements. Alright. Another example of mathematical statement would be there is the largest natural number. Before we decide if it is true or false, reminder, natural numbers will denote them all together as such thing. Right? Okay, natural numbers, those are numbers of a kind. This is of course false. Because suppose n is the largest, then we know that n plus 1 is also a natural number, right? We know how natural numbers behave. Also a natural number. So n was not the largest number because it contradicts the circumstance that n plus 1 is always also a natural number and was not the largest. Since we could do it for each n, any natural number, we could just add 1. We have that there is no largest natural number. Right. Alright, that is a mathematical statement. Simple definition, right? But you have to be careful, right? And always keep in mind all the attributes of what being a mathematical statement is. It's a statement about mathematical object that has exact interpretation and about which can unambiguously decide if it is true or false. So only 2 possibilities, true or false, nothing in between. This is just how it is defined, and in mathematics we only work with such statements. Okay, so the pool of these statements which we use in mathematics is restricted to such objects. So our whole mathematical language consists of such phrases when we talk explicitly about mathematical relationships. Because talking about mathematics is talking about mathematical relationships between mathematical objects. Right. The accompaniment is nothing but the narrative which allows us to come up with the story written in mathematical language. Alright. So from now on, let's call it notation. We give some nomenclature to denote the further introduced statements, and that is of course mathematical statements. We denote them by big Latin letters. A, B, C, D, and so on. Right, but we will not need many letters for those considerations, as you will see. Alright. So, next we come to some formal operations on mathematical statements, and that is mathematical operations on statements. And they will kind of resemble what we have in the natural language, but they will always have to satisfy this requirement of being exact and unambiguously true or false, and of course having mathematical objects and their subject, in this case mathematical statements, since it is operations on statements. But you see already, I talked about it like they are themselves mathematical statements, and indeed mathematical statements, all mathematical statements are mathematical operations on mathematical statements. So we can inductively build an ever more complex structure. Okay. A common feature of mathematical structures. Phonetic operations and statements. So, that's one introduction to mathematical logic. Okay. Let's call that section 1.1. Let's call that section 1.2. And that's in 1.2.1. Mathematical end. We take two statements and connect them by the end. We write it like this. So this reads read A and B. So, and this is mathematical statement A, mathematical statement B, and we connect them then via end, and we get mathematical statement A and B. A is chosen arbitrarily, B is chosen arbitrarily, so we can connect any two arbitrarily chosen mathematical statements via this end. Now, be cautious, there are two levels of interpretation. If we stay in the abstract realm of mathematical logic, the only thing we are interested in is how the operators work on the mathematical statements with particular proof values. When we switch to the genuinely mathematical view, the statements will have their own contents, and then their contents will decide about their proof value. But how the operators work, they will still only work with truth values. Alright. Note mathematical operators. Only care about truth values of inputted statements. What do we mean by inputted? Well, you see there we connected A and B via AND, but actually here is a slot, here is a slot, here's AND, here you input a statement A, here you then input a statement B, where you can choose A yourself, and it has to be a mathematical statement according to the definition above, and you can choose B yourself. Right. Only care about true values of inputted statements, but not about their content. So the content of inputted statements is irrelevant for mathematical operators. We work with inputted true values. Very important. They can be seen as machines reading true values of inputted statements and outputting a true value based on the read values. So, example for AND. Example that exemplifies this explanation. Input AB goes to AND. Well, I could have denoted that also like this, right? Doesn't matter how I denote that. The only thing that matters is what it means structurally. And here, to be more precise, well, AND reads those things and gives them truth value. It reads the truth value of A. It reads the truth value of B. That is the reading step. Here is the output of reading. And based only on that, on all things, it gives some true value, right? Okay, so we don't care about context. We have some machines that read true values and spit out true values, right? But now, this is a video of strict mathematical logic. Determine the true value, which are three true values. Nothing else, no context. Now, second layer. So A and B is actually a statement with a content interpret derived based on contents of A and B. But the truth value of the statement with that content is determined entirely by the machine function of a logical operation. Applied to true values of input and not based on some clever thinking. Intuition, or whatever else. The true value is determined according to this procedure. So, to know the truth, which in mathematics means the true value of that composite statement, what we consider is the true values of input and what the operator by which we connected the statements gives for those respective truth values. This is the only thing that determines the truth value of a composite statement, and not some clever thinking on our part disregarding what is happening here. This is mathematics. We have strict rules to obey to structure our thinking in proper way. Right. Of course, subsequently, it is done more and more intuitively, and one is allowed to resort to more flexible reasoning. But intuitively and automatically, one always is guided by this scheme. So what would seem like resorting to intuitive reasoning will be truth application of this scheme. And what exactly that means, you have to find out on your own. No one can explain that to you. We can only give some guidelines that we regard as sufficiently clear to enable you to see the true picture of how it works. No one can describe the whole true picture. You have to do work. You have to find out by yourself how that really all fits within mathematics. Right. Okay. Let's investigate those machine functions. Well, the definition of operators is of course based entirely on those outputs for the truth values of inputted statements, right? Well, that is, we have to consider all possible combinations of truth values that could be inputted. Well, we know A could be true or false, B could be true or false, and all combinations are of course allowed, because we could just choose this statement arbitrarily, so we could actually meet any combination. Right, so everything is allowed means let's go for all combinations. A is true, have fixed that. Then B could be false, or B could be true. For saying A being true could be those two options, right? We could choose the statements in that way. We have to consider all combinations, have to define it for all combinations, because we want to have this procedure. And so for any combination, we want to have this truth value, right? And we define those mathematical operations or operators just in a reasonable way. That it is reasonable, the practice has shown by some things, for example by and. You can also see it from everyday intuition, but generally the justification is praxis has shown it works well for our purposes. Right, now the definition comes. So we take this input, here is and it connects with A and B. Now suppose the input was A was true, B was false. What does that do? Well, this means that both is true, and only in that case the output is true. So it is an indicator of A and B being both true. In our case, it just gives false, so those cases are indistinguishable. So that is an indicator that shows this case actually. It's exactly the indicator of this case. All our cases are just false. Right. So A and B means both. This also aligns with everyday intuition, right? Alright. Next up, 1.2. Definition of OR. Denoted for the two statements as such a turned upside down head. Right here I could also write, and this equality we don't know yet what it is. Abstract equality, just meaning I denote the same. I could have written that, right? Or what's that? By the way, this thing is called a truth table. Right, a truth table for the mathematical operator. And here, see, we could have any input values. We have to take all possible combinations, and we have to specify what OR does for each of the combinations. Well, OR signifies all the cases when at least one is true. So both true is okay. At least one true is okay. This is not okay. Right, and this is just definitions. So this you could call including or, so it includes the case of both. It is not excluding or. Also aligns with everyday intuition, but not by all mathematical operators. It would be necessarily the case. Right. And you should meditate looking at this and should memorize it very precisely, because it will be everywhere in the subsequent considerations, even though I won't refer to it necessarily explicitly. As I told you, with time, if that happens comparatively fast, we'll use that all automatically, knowing what we are doing according to these words or explanations here. Right. Definition of not. This is one position operator. It takes just one logical statement. What does that do? Oh, of course, it turns its given value into the opposite one. Right. And here, pay attention. Those can be seen as signifiers, right? We have some truth. But here you can't really think of that. We call interpretation layer. Interpretations, mathematical interpretations could be here as signifiers, but here it would not reasonable. It would be not reasonable to think about interpretation. It's more like what it does to the statement. Right? But again, it just takes the value and turns the value upside down. This is what the mathematical operator does by definition. But of course, on the level of interpretation, that would give some statement, and we will learn how precisely to invert statements in the mathematical way, how to invert mathematical statements. It will be not necessarily always obvious how to do that. Alright. And again, another emphasis, you should memorize those notations, should internalize them, and you should internalize those kinds of behavior the particular operators exhibit. Okay, then definition of what comes now. That was all. This, I think already that. Definition of implication, or it follows. Again, despite that suggestive notation, which also will mean exactly that in mathematical interpretation, this is a mathematical operator. That is, it takes the two inputs, and just forget for a second that it is suggestively notated. I could denote it like that. And it is not W, this is just two turned upside down heads put together. Put together on one side. Right? I could denote it anything. So forget that it is an error. It is just, it takes some inputs, gives some outputs. That it is an error, that is a level of mathematical interpretation, that is another level, which is also interesting, but for truth values, it just takes some inputs. Alright. The definition is, again, we need all possible values, of course, because we want to know for any possible input, which means, since we only regard truth values being mathematical operator for now, which means we only need truth values, specify all possible inputs of truth values. And here is something which might seem counterintuitive. That is defined to be always true when from false something false follows, but it is just operator, remember it. Why this mathematical interpretation actually works, so it signifies everything. And in this case, it doesn't work. So why? Because this is the only case which we want to prohibit in mathematics. From a truth must never follow something false on the second level of interpretation. If it does, then the implication is already false. In all other cases, that is allowed, so we do not exclude that the implication on the second layer, on the level of interpretation, that the implication might be true when from false follows true, from false follows false. So we kind of make our life more difficult in setting this, but this is why? Well, because this actually is. When we go to the level of interpretation, this might happen. We might have a false truth, and we might have concluded something true from it. This is possible. It is really possible on the level of interpretation, on the level of logical reasoning. This can happen. That is why we don't exclude that. So, on one hand, this is just a definition, and this shall be regarded as just a definition. But on the other hand, this has some history, and the history is that that can actually happen, and we want to keep in line with what is actually happening. But formally, it is just a definition. Right? And this is called, this also has a nice Latin name, ex falso quod libet. On the level of interpretation, from the false you can conclude anything. Ex falso quod libet. So just note that it works in the sense of mathematics properly. It is just how we deal with mathematical statements being led by this. Right? And it turns out that this definition indeed gives a consistent picture. I don't give at this point some intuitive examples like there was a rain and the street was wet after the street was wet. There is no after rain. It was rain. The street was wet. You probably have heard this example follows, and that it is kind of intuitive. No, I don't think it's proper thinking about that, because the truth of the matter is a mathematical statement is a statement about mathematical objects in the realm other than mathematics. It doesn't say anything and it doesn't have any meaning. You can translate it sometimes, but the truth of the matter is this is just some narratives that do not have any solid justification. Right? The solid justification is this is defined like that. Alright. And this was just to illustrate. Right. It takes us to its input and connects them in that way, which we have here as input truth values assigned true. Right. Okay, finally, we have definition of equivalence. And that just signifies the statements are logically equivalent. Well, what is logically equivalent? Well, by application of operators, we only care about truth values. And this appears also here. So, true, 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 false, false, true, false, false. We take this as an input, here we. So it signifies the equality of the truth values of the inputted statements. This is definition of equivalence. Now, after we have seen that, we can kind of do computations with those things. In certain ways, we can do computations with those things. Right, what does that mean? Well, first of all, let me introduce a proper section. That was 1.2, mathematical operations and statements. That is 1.3, basic identities. For mathematical operations. And statements. Well, what do I mean by that? Well, recall that all this gives a statement with certain truth value depending on the truth values of those statements. So it is a legit statement. Since those were exactly interpretable, this will be exactly interpretable, and the layer of interpretation. It will be exact, since both are exact, and the operation is defined to be exact. And this is just what we assume, but it works in mathematics consistently. And it has well-defined truth value, meaning that the truth value is already exactly determined by the input truth values. So this is indeed again a statement. If it is indeed again a statement, then I could have composite statements, right? And I could have here another statement, for example, C. So I connect this statement because it is a statement, so I can take in particular this statement as a statement, and I can apply to those two statements the mathematical operator it follows, also called implication. Let's denote it here. Okay, so I can do that, and also I could do more complicated things like, I don't know, I could also repeat some statements because nothing prohibits me from doing that. I could also consider something like that. No problem with that. We just have those mathematical operations. We have the parenthesis, which denotes, as always, that we take that first. We make out of it a statement, and then we apply this mathematical operator to the statement that results and to the other statement, right? And we could just have some slots and all reasonable expressions, right? You did like that. All reasonable expressions where we could fill those slots with parentheses and uh, some statements that are all possible, right? Where we could fill it reasonably. So this reasonably led, right? You don't need to think about it explicitly, just think about us building different things, defining statement by statement, one after another, just taking such elementary steps. So we could build arbitrarily complicated statements, right? But now some of them simplified. Recall that the results of mathematical operators are simply the truth values. We only care about the resulting truth values. That is, by such composite statements, if we talk about calculating with mathematical operators, we only care about the resulting truth value. How do we compute the truth value? Just step by step. But they are shortcuts. And those we will consider now. And are commutative. And associative. What does it mean? Well, that means, and here I have to introduce something on the layer of interpretation. This actually obviously means kind of equality, since we only care about truth values. Such statements where we use mathematical operators or where we compare statements in the logical setting will be equal, what we want to regard as equal, when their truth values are equal. So this is equality of logical statements because it signifies exactly the equality, right? So it will be And by the way, equivalence is called if and only if. And a shortcut, we write this as if. Right. So this is if and only if. Now in the standard sense of intuitional understanding, this is if and only if. So this statement is valid if and only if we are, in the logical sense, the statements are equal, that is, have the same truth values. So this is kind of equality for those logical statements. And so why I had equality for a logical statement here, I actually would have to replace it by this equivalence properly. Now you can see that. But okay, since it is just notation, there's no need to but yeah. Okay, a commutative and associative, and that is equality that, if you recall what parentheses mean, they mean the order in which it is carried out. That is associativity, so we can move around the brackets, and by induction and considering different cases, you actually can show that if you take an arbitrary number it simply doesn't matter in what order you do these statements. So this can be regarded as just such a statement where this is just I.I or I.II or I.III, and you could put the parentheses in any way possible. But customarily, it's not proved, it's just considering all different cases and using induction. Right? I mean, it results from that, and that is what usually is proved. Alright, that is associativity. And commutativity, you probably guessed. That this is the same as this. Also write it in over down right, equality is symmetric. And of course, here again, you could just have just written, and here, of course, also same with and. So if you take again any statements, you just get that, right? And commutativity again, that is already sufficient to conclude any rearrangement. And I mean by that, of course, of order. For example, something like and so on. Same for the end, right? So that, to prove that, suffices to already have full freedom of interchanging if we have only this separation in between, and having only that already suffices to full freedom of putting away parentheses. That's why we don't put them anymore by such expressions. Right, and until now you have only seen how we use those tables to define things, but now we will use those tables to check things, right? And this is our first proof. And this is proof by truth table. We just have to establish that. That is, we have to establish that this is actually true, right? We have to establish truth of this equivalence. So second layer of interpretation, the direct interpretation, have to establish this equivalence. Then, in the logical sense, the statements are exactly same, right? Meaning their truth values are same. What do we have to establish for that? Well, we just have to show that this will always result as true, independently of what values we have put here. And since that is same statements, this is what we are trying to compare here. This is same statements, this is same statements, but the operators are applied a little bit differently because we first applied that here, and first we applied that here, right? So we have to compare if we would get that this equivalence is always true. If it is always true, that means that we always have a case that the logical values or the truth values are same, right? Because this is the only case when that will be true, no matter what values, but they are the same. This is the only case what we care, and this is the only thing about which we care by talking about equality of logical statements, right? So proof, and we only prove that one because the other one is just homework, right? So we now use the truth table to check things. How do we do that? Well, only one time I will do it very carefully. After that, I will do it very fast. You see, again, we have to consider all combinations, because for all possible input values, which are only relevant is the truth values, as we know, because that is how logical operators work and how the compress works. On the second level of interpretation, in what we are interested by comparing the statements within the realm of logic. So we have to put in all the possible combinations of truth values. How do we do that? Well, fix A being true, and B could be true or false. So fix A being true, that is fixed. And then we have to consider all combinations here to already have done the combinations where A was true, right? Here B could be true or false, and for each of the choices, true or false, C could be true or false. So fix for now B true. Remember that we have fixed A true and we have fixed B true, and now we have two choices in C. So this is still fixed. This is still fixed because we haven't yet worked through the choices here. So now we have worked through all the choices here, right? Here we have worked through all the choices, so this slot is finished, but this slot is now still unfinished because it was we only worked through true, so we have to work through false, and we are still in the case of A being true, so A being true is still fixed because we have not finished working through this slot, right? And now we go through this slot again. Of course, we have those two cases. sorry, we are still in the second slot of B being false, because we have two cases here, and the other case is just this. So now we have finished work through slot B, because we have finished working through true for B and working through false for B. Now we have finished working through A, because we have finished working through B. And that is A now with the changes, and of course all the same repeats. You can just look at the same dynamics. And can figure out for yourself that it works. So this is really all possible combinations, because we have worked out everything by fixing the particular things, right? Particular things, always another things, which gives us that all combinations have been worked through. And you can also think about it combinatorially. We have 8 combinations. Right? Okay, have to check it. Okay, just if I copy it, right? Right, have 8 combinations, because we have 2 possibilities here, 2 possibilities here, 2 possibilities here. So 2 by 2 by 2, 2 multiplied by 2 multiplied by 2 is 2 to the third is exactly 8. And we have 8 combinations, and you can check that they are all different, but they are just all different by the way how we have closed our particular slots, right? Right, so, and I told you that I will do only one time the careful calculation. A careful calculation would be now, in the end, we want to compare what? We want to compare those two. We want to have their truth values. And we want to have it always being called true. So and it's somehow it's separated from the proof. Right. So proof, and that is proof of the first one. Right, that is the first one. Right. We want to have that this always has value true for everything. And we have to check if it is the case. So let's do it. For that, we have of course to consider those things. I have to look at their respective values. So what is participating there? Well, as I said, we will just check it step by step. And I repeat, that's the only time that I do it that thoroughly. In our case, I will just evaluate very quickly, for example, the whole statement here and so on. Right, but at least one time, let's do it properly. So, and after we have evaluated those two values, we can take those two values and just take two values of that, which we have computed from here, and we can take two values of that. So right now I'm just preparing the stage, so to speak. The other thing, this here, we need this two value. and we need then to put it together with this two value A. Right, let's just do that. Oh, just recall the definitions. We have AB, we have OR. OR signifies what? OR signifies the truth of at least one. So, correspondingly, whenever at least one of those, pay attention what we input. We input A and B. And at least one of those here is true. I have to put true. And only in case when it is not the case, I have to put false. Anyway, let's do it even more properly so that we don't get confused by our own entries. Right, I have just used the definition. This is how easy we evaluate the truth tables. Now we have that L as promised, and we just have to compare it with C. So here we have again OR, and I have to put true everywhere where we have at least one true. For comparison between those, so I look only at those two, right? Alright, the result is that false. Right. Now here I have to look at B and C and do the same thing. Not explaining it anymore because I've already told you. And pay attention, we are only interested in the final statements, so how the comparison in between is, or between some different columns is not interesting. It's only interesting to compare those two because only those two participate in here. And those are just intermediate steps, which I'm doing here. Now compare that with that for that, right? So I'm comparing that with that, right? Right. And whenever there is this one of both is true, in this column or this column, I'm putting true. Otherwise, false. This is only one case when both is false, and it's otherwise here. And here, okay, only one. Oh wait, I have mixed up the column. That is by the way, yes, you have to pay attention. I'm not allowed to mix up the columns. So we compare that column with that column. So yeah, also on that big screen, this a little bit problematic, right? So only the last is false here, right? Otherwise we have true. Right, now compare those two, because this is what this here does, and we see same. So here will be true, here will be true, here will be true. But we could also actually omit this, and we could just look at those values. Those values, compare those values, and we see if we all correspond, which exactly means we prove that, then we are done. But now we have written that, so let's do that. So that was very easy, right? Just three definitions, basically without thinking. So comparing this and this, comparing if the values are same, because the equivalence signifies exactly that, signifies means it's true when, so ff t t t t t t t t t t and so on. So this is indeed logically equal, meaning giving same true values for any inputs. Right. Two is homework. 3 is homework. Because it's just that. You have just to be careful, to pay attention to what you're doing, to pay attention to what columns you are comparing, but other than that, it's nothing, right? Of course, it might seem like a lot, it might seem like abstract things, but you have just to be careful to know what you're doing and what you're doing is based on and how it should be carried out. It is based on the particular definitions, right? So let's just trophy commutativity. And as I promised, I won't read more into it that extensively anymore because it's very simple. I'm just doing everything that I told you above. So it doesn't matter in what order I compare, right? Only the total comparison matters. The only thing is I have to have taken all the possible cases, right? So, and that is just end. So that is false, 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 that is true. And that is again just you could already have seen that immediately. False, 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 and that is true. And then those both are equivalent, so yes. And the proof is finished. And when a proof is finished, we denote it by such square, point and square. Right. Right. The proof is finished, assuming you will do the homework. I will believe it, but I would not recommend it. Alright, 1.341. One point three one two. We also have equivalence of if we want to break it out, like to put it in 2, then we have to pay by it by changing that mathematical operator to this mathematical operator. Same here. We only prove 1. That is also called De Morgan laws. Proof 1 all F.E.V. have all possible combinations. And as I promised, I won't anymore do that step by step, fashion wise. I will do it right away, but you can do it step by step if you wish. Right? That is false, false, and end of false, false is false. This is just something that will some of that will turn to false. So this and this is end, so this will be false. Again, here which will turn to false, and we have end, so this is false. Here both will turn to true, so that is true. right? Here we took here everything false, right? If we look at that, and here everything is false. So it is all truths. And here we have the false. Alright, it doesn't look like it works, actually. Something is wrong. Of course. I see here. If I put another thing, then we have seen it doesn't work. Also good. But okay, it's not what we wanted. We wanted to check that. Right, you can see that here. And I have put end. Okay, so or so this all is true. This all is true because we take or, and this is not, sorry, not true. Here we take or, false, false, so that is false, not without true. Okay. The other thing you could do same way, or you could say and here you will already encounter a little bit of level up in how we think abstractly. Many steps at once. This would be just kindergarten, but here you will already maybe be troubled, but well, just you see, when we take that, and this is same, and this is same. Why? Because A is same as not A, and B is same as not B. That is very simple to see, but if you don't see it, think about it with truth tables, and really do that if you don't see that. So you see, of course, if those always have same truth values, which this means, then I can replace that by that because I'm only evaluating truth values, right? So if that always has same truth values, that I can replace that because I'm only thinking of truth values. So this means this consideration belongs to this to justify this. Right. Now we have done this, and we can think of the statements not A and not B. And we see that those statements are connected as not A, not B, and they are connected by and, right? So we already know from the first one that this connected by and, not here it was A, but here it is not A, not B. Okay, I will do it easy for you. This is a statement, this is a statement, and this just gives a structure, right? That it is now A, it is not A. It's just a statement. That statement could be not A. That statement could be not B. It's just about structure. This was equivalent to this. So applying that to those statements, you obtain not. This is not before the bracket, and here inside that I use this reasoning and I obtain, of course, since I'm applying that to this, then I have to take the notes. I have to take the notes and I have to compare them by that, by or, because those are the statements that I'm looking at. So we have not A, not B. So that is we not. And here we have not A or not B, right? Because those are the statements we are looking at here that are not here and uh, are connected by this. And here we have just this is put in here, and this is those plate the rows of A and B. So we have to put it inside, and we have to put it here, and we have to put not before that, right? But we already know what that is from here, so that is just not A. I mean, this eliminates each other. Not is known from here, and so that is actually not applied to this. It's not A or not B, which we wanted to prove. Here we have that. Here we have that. Right? And now we want to prove exactly that. Right? So you see, maybe you can't follow it all through in your mind at once, but you can follow through each step. And if you can follow through each step, that means that this reasoning works. And in mathematics, you might have proofs with hundreds of steps. You can work through each one, but you will not necessarily be able to keep in mind the whole sequence of the 100 steps. So that's normal. And this is a little bit abstract, I know, but you just have to think of structures, what place, what role, and what can be chosen how. Because this P could be chosen as not A, this P could be chosen as not B, and then you just have to see what structural roles they played and how it is reflected here in what I'm doing here, right? So this indeed proves that. Or if you want something easier, just do this business, same business. But I just wanted to give you a taste of getting more abstract, because that will be pretty common. Alright, that is the Morgan laws. And now we go to 1.3.3, and this is kind of distributive law. This kind of distributive law. You recall distributive law, side note. You recall distributive law from the new numbers, right? From the school, the numbers were allowed to be calculated like that, right? Those calculations were allowed because equal. And here this distributive law is just mathematical statements have both things. And again, those just play structural roles. It could be any statements. Okay, let us prove both. Sorry, I have not even written what is happening here. Of course, distributive law, so what could it be? Pay attention, both. So they are not kind of like multiplication and addition, but kind of like something different. Because that, because I'm taking that, and then and a short reminder why we take that. Well, in complicated statements, we'll be able to replace one with the other, because if the truth values is the same, and of course the truth tables by evaluating will give just same if we replaced one statement by the other equivalent statement, because that's exactly what equivalent means, right? We define it like this, right? Equivalent statements can be replaced by each other by dealing with mathematical statements by evaluating their truth. Very important note. Okay, proof. Well, again, I won't be that thorough as I warned you, because it's really simple stuff. You just have to pay attention to what you are doing. Okay, that seems to be all. And we are in the first one, so let's consider consider right. What do you have to look at here? Well, AB, A or B, true, 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 and true, true. Here, A or B, true, true, and false, false. Here, true, here, and true. Okay, here, true, and false. So when C, one of the constituents of the true, is false, then we have already immediately false. Right. In our case, we have to look. Here we have true, here we have true, because here we have or, right? But pay attention what we connect. Here we connect A and B. So, right. Here we have true, and this constituent is false, because we have or false. Right. Now here, A and C, true, true, are true, true. So I have mixed up, yes, you see, A and B, but now A and C. Okay, A and C, true. B, of course, that's wrong. What we are interested in is B and C. Right, right. Okay. A and C, B and C, true, 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 true. Okay, at least one has to be true, otherwise it's false. And what does it mean? At least one has to be true. Well, that is either A and C have to be true, or B and C have to be true. That is the only case when we have truth. So it's exactly the case when we have truth. And just interpretational thinking for the rules with logical statements, right? So A and C, B and C, A and C, B and C, A and C, B and C, right? B and C here. Here, or well, both could be also, okay, but at least one has to be both true. Or A or C, both true. A and C, both true. Or B and C, both B and C, both true. Right. Not the case here, 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 but pay attention to what we are comparing, because it is really easy to switch to comparing, for example, like that and like that, but we compare like that and like that, right? So here not, here not, here not, here yes, B and C, here not, here not, here not, here yes. So that's the truths, ours are false, which indeed compares to that exactly. So we have proved that. Alright. And the second one, and you can check it more precisely if you like in more steps. There's no need for that. But, maybe in the beginning there is, because you have to get familiar with that. You have to be able to do that just like nothing. And I mean, not only filling out this. Okay, what do we do? Well, we do this distributive law. Okay, in B or C. And here we have corresponding A or C and B or C. Right, just the same, but the rows of and or are switched, meaning the bracketing is switched, and yeah. So A and B or C. Right. Right. Of course, we could try to play with it a little, but I think it would be easier here to just do the truth table. And to play using De Morgan laws, for example. And with a statement, but I think it would be easier to fill with it. And you already see there could be many ways to prove it theoretically, but I'm just choosing one of them. Okay, so if that is at least A or B is false, well, it doesn't mean anything, so that is true. If it don't leave, A and B are true, or C is true, right? Right. Or both, but of course if I think or, then it is also included both. Right, so here is true, it is true, it is true, here it's false, here it is true, it is false, here it is true, it is false. Right, just using the reasoning I just mentioned. And you can think about why this reasoning works and just using the definitions. And here the comparison, well, both have to be true. For that we have to see, and we have to have that C is true. C is true is one case. Well, I mean C is true and something else, no matter. C is true works. C is true, or A is true. Okay, there are different cases because C is true is one case, yes, but other cases could include different combinations. So, okay, all cases with C is true are already given, and then the opposite case is C is not true. When do we have truths nonetheless? Well, only in the case when A is true and B is true. So C is true, or A and B are true. Okay. C is true. C is true. B false. False. Great. And we see that's same. And we have already kind of seen it from interpretation. Not really, but yeah. Alright. Alright, this is how we prove things with truth tables. One country confirm representation of implication. And since I'm not sure, I believe not binds stronger than other uniters, so it is customarily not to write parentheses are not, because this is always done first. If I'm writing this, I'm not doing this. I will prove that in order to see if I actually got it right, because because it's like it's a little bit confusing maybe, but you could think about that if it's even right, and then it is reasonable. But let's just prove that. Okay, what you call the only bad case is truth can never follow something false. Here, not a false or true. False or true, at least one is true. True. Here, not a, so that's false. Not a or not true, false, false, false. Here, not a true or true, true. Here, not a true. So, indeed, that is truth. That is truth. And you could think about it, or you could just accept it. That it works like that with arithmetic operators. Even if it would make no sense, that would just be the consequence of our definitions, and then it's valid. Right. Alright, 3.5. Equivalence means implication in the one and in the other direction. And here you can see very nicely that the meanings can be applied to the meanings itself, operators to mean something about operators. You see here equivalence is equivalence of two statements, but now we take that as a statement, general statement, and we say that this statement of equivalence of any two statements is equivalent actually of course not or could be wrong, and it's equivalent to this statement. So this is equivalence between statements, but this is using equivalence to compare the statements and to have this general claim, right? But doesn't matter. You just write it down in the truth table and you see that it works, right? So you already see that things can be applied to things itself, and the layers of meaning, or the levels of meaning, can be brought to higher heights, because that is the first structural level, right? And now you claim equivalence for the equivalence itself. It's kind of equivalence explains equivalence, but well, you don't have to think about that, do you? Just imply that you have that, and it is on the level of interpretation. It is very natural. It just means that equivalence means implication in that direction, simultaneous implication in that direction, and in truth logical sense, well, implication in that direction and implication in that direction just means we can go both ways, right? With that and that, but if that and that, and in the logical sense of truth values, this makes pretty much sense. But don't think about that too much. Just use the truth tables and you'll establish that, right? And I don't want to write any more truth tables. It's rather trivial. Instead, you have more work to do, right? But it's really easy. You have just to write truth tables, you have to look at that, and you'll see that it actually works, right? Okay, and probably the last thing, contraposition. This will be important for a certain type of proofs. A implies B is true if you don't live, and that of course you could also read as is true if you don't live. And you understand what I mean by that? Actually mean that the implication from not B to not A. So normally you would write it switch like that, and you would write an implication in this direction, but I have adjusted it differently. It doesn't matter, right? Right. So in our direction, we could also consider application of the worked statements. So statements work to the opposite, but then it has to go to the other direction. Right. That is contraposition. Proof homework. Just draw truth tables. Write truth tables. Analyze truth tables. Right. I think this is it about the mathematical logic. We actually do not need anything else, I think. Logical operations and statements. Alright. Introduction to the math logic. Next up. You should really internalize this chapter. You should do at least some proofs. To understand how it works, you should really internalize and think about what makes sense, how it works, what gives what structure, how these structures are interrelated, and so on. Right. Now, next up. To production. To the set theory. Free. The quantifiers. For the maps. 5. I don't know if I will do it in this course. Accountability. And accountability and equality. Or cardinality. Etc. 6. Mathematical induction. So okay. Don't know. Okay, so customary notations, summation, product, etc. And of course that could be different places and could be switched in its order. Right, I don't know yet. Okay. Oh, let's maybe start your introduction to a set theory. Definition, set. It is a collection of clearly defined distinct mathematical objects. A set only knows if a mathematical object in the object is inside of it or not. It has no other properties. For each object, it tells you it is inside of me, it is not inside of me. That is a set. And if it is inside of the set or not is a mathematical statement. So it is either inside or not inside. So inside of a set is the being inside of a set is either a true statement for your object or it is not. And this is how a set is defined. This is what is behind this definition. We denote sets by different symbols. You see different symbols and notations. Notation for a set M, write X element M if X is in M or belongs to M, just like here. As it knows if the mathematical object inside of it or not. If this set is so that X is in M, we write like that. Otherwise, and we have only those two cases if you recall. So X is not in M. We write that. Right. So for any object, we can either say that any object X, any given set M, we say X is in M, X is not in M. That is, if we think of a pool, and here in it are all mathematical objects, I denote them by points, then a set goes here and says, this is mine, this is mine, this is mine, and so on, and the rest is not mine. And this saying what is his is the being of a set. Right. It's its very essence. And nothing else. Exactly that. Now, if we'd like this again notation, right? Like, and let's also code accordingly. If we like to specify a set with given elements, that are explicitly given, with given elements that are explicitly describable one by one, in their totality. We write A, B, C for right? And this is just an example. And it works for other numbers of objects. Okay, we see for a set containing exactly, and we always have this exactly, right? Recall what a set was, what its essence was exactly in mathematical objects. A, B, C. And mathematical objects could be anything, could be other sets. A set is a mathematical object, so could be just anything, could be a set, number, and something else. All possible, right? Caution. A name of a mathematical object is just a reference to it being a row of its substitute. Since we have to refer to it somehow. But in truth, consider the following example. Example, take the mathematical object number 2 in 2, 4 minus 2 the smallest even number not equal 0 and countless other differences. Describe that same object. So when we talk about name, we talk about name. But a set is a collection of mathematical objects. Well, we are humans, we are limited, so we actually use references to say that the set includes objects. To put object into a set, of course we can't touch its pure mathematical structure, but we just give this object a name, and we put this name into a notation of a set, but we mean that the object is contained in it. Right? Sets but be very sets contain mathematical objects. Not here. Names. So when we write something in addition, we said we just refer to the object. Thus, so it's all same sense. Since we are interested what objects are in set. And this is just calling same object by same name or by different names. And by objects we mean, of course, mathematical objects. Alright. Alright. This is a possibility within our sets. So examples of explicitly denoted sets. Okay, that's examples of sets. Now, in our notation, if it is clear how it is clear what our objects are in the set, from specifying just if you denote of course this is same set as right. This is the set of all even numbers starting by 2. And this is so suggestive that it just goes on forever because we have not given upper bound, right? Could have written differently, but I don't want to. Also self-suggestive, right? So, and of course, it is in the eye of the beholder what is self-suggestive or not, but usually it works in mathematics, right? So everyone understands it's meant. Usually we do it in a reasonable way so that it is understandable what is meant. Alright. That is said, and now notation. We can also specify things. By describing defining properties. It's like K in N. Do you recall that notation, right? K is between the numbers 2 and 4. And we read it like that is a K in N such that it satisfies this condition, and that is exactly all those keys in N that simultaneously satisfy this condition, simultaneously with being in N. So if we write this, we write here a condition on the element, right? So that would be exactly 2, 3, 4. You can see, right? Or X such that, of course, we mean X, for example, and right. So usually by such notation we specify some larger set here, and we specify just what elements of this larger set we'd like to have, right? And here we have already introduced notation sets of numbers. Well, I think you should know them, but just repeat it. N is the natural numbers, and in our case we will produce 0. Z is just union of n and minus n. Okay, we don't know the union yet. Okay, sorry. Have not introduced it yet. I'm too fast. D just circle to go both directions by 1 steps. Right. Those are natural numbers. Those are integers. So, and that sign means I define S. And here we use this notation, that notation by descriptional property. How exactly? Well, here we just say that this is, and you see here I have not given a larger set because it will be obvious just from here. Right. But actually in the proper way I would give it still, because if we don't define it where it happens, then it could be problematic, but I don't think about it much. And P is of course not equal to 0 because we don't want to divide by 0 with assertion numbers, and R all numbers at school before complex numbers. Of course, it's not a proper definition, but you understand what I mean. You could also say, well, any decimal number, that is in particular those with non-periodic numbers. So that is, there's no remaining period after 0, but instead there's 0 point, but instead there is something that never becomes periodic, so just some numbers. This is not real points, like it is clear how it goes. No, it is not clear at all. So any decimal number, all the numbers in school, right? Alright. Definition. Empty set. As we said, elements. And by the way, what is in the set is called element of the set. Elements denoted. The set is denoted by that thing. Okay. We have already used a little equality of sets because it was kind of self-suggestive, but actually we have to define it properly. To that we first need definition subset. We have subset of n, and this is how I define that notation, and I define it via some truth, and the truth has to be like that. But that is always a true statement. And here you can see how implication works. Well, we are actually only interested in the case when the statement is true. All other cases just nothing, but the proofs might be of importance that we don't miss set of track. When something is true, it does not say anything about the premise by which it's stated, but here only interested in truth, and so in truth we would never have false if implication is true, and we want it to be true, so that is how we define it. If we just state implication somewhere, then we mean we want it to be true. And we have that the truth of this really implies that, and we want implication to be true, that is, we want that to be true. So we want to have now a second layer, the layer of immediate interpretation. We want to have whenever this is element of n, that is true, and this is element of n. And we denote it like this. Right, and here you see I already used as logical statements, pretty self-explanatory, so I'm already having some abstract objects here. I'm defining it like this, yeah. That's why you should familiarize yourself with them properly. Right, definition equality of sets. So what we used here, just thinking we know what we think, but we didn't know what we think. But luckily, it works on this equality of sets because it covers all the intuitive cases. Equality of sets have when both is true. As you see, I'm already using those statements on a higher level and just logical operators. I'm using them where already dealing with mathematical objects, stating some things explicitly in statements, not in abstract notation for statements like there is a statement, but this is an explicit statement and I'm using that. Right. This again inequality. Two sets are equal. One is a subset of the other, and simultaneously the other is a subset of the first. Right. Right. So anyway, here we have interesting corollary of definition. Or you could also say corollary of definition of implication. Definition of implication. For any being a set, have that the empty set is actually a subset of that. Proof, well, we have to prove the truth of that. And now you will see that implication is defined in a very convenient way. First with like empty set to be subset of any set. And now proof. Have to prove truth of that statement. But is false since contains no x. And we know it is either or. For in x it is either contained or not. And we see that this is our statement, and this statement is false because it contains no x. And so for any x that we take, the answer to whatever it is contained is not. So this statement is always false no matter what x we take. Then and now recall the truth table of implication is true. So whatever weird object empty set is, just by definition, it is now subset of any set. Just by definition, just to be that. Maybe it is weird, but you'll get used to it. Okay. Now, next up, operations and sets. So, you should take time to internalize all the things we have done. It was quite a little bit. It might seem very simple. It might seem very difficult. It doesn't matter how it seems. You should internalize that. You should understand what we are doing, why we are doing that. So don't try to somehow force yourself to understand things where nothing is to understand yet. Be cautious but careful with yourself wherever there is need for understanding, there is not, and things like that. Of course, I can't explain you everything, but you just have to think and find out. So it's trial and error in many ways when you are trying to develop a strategy how to deal with mathematics yourself. Right. With that, I'd like to finish for now. Next time, we'll continue with set theory. Right.